I've seen here most people come from the database side, whereas so this work kind of came more from the knowledge representation and reasoning side. Just to give you a very brief background information, so I'm part of the knowledge representation and reasoning group at Oxford, which is run by 3 academics, Ian Horrocks, Bernardo Cuenca-Grau, and myself. And as Nas already said, we were doing mostly DL-style reasoning, Tableau algorithms. We were heavily involved in the development of OWL2. But then, recently we moved more into this kind of RDF graph style, applications, and more, let's say, merging this knowledge representation on the one hand with the database ideas on the other hand. So I'll just take a little bit of time to tell you a bit what I've been working on in the past 2.5 years now. The outcome of all of that research is a system called RDFox, not RDFox, so RDF Oxford. It's basically a, RDF triple store with some new features or some kind of different technological approaches, which I'm going to talk about. So here is briefly what RDFox is. It is a RAM-based system, so we don't persist data. You can persist data on disk, but only as an export, and then you can start from that, but we don't actually do any kind of on-disk persistency. And this is simply because current systems have really lots of RAM. 5,000 pounds. Recently bought a machine that has 256 gigabytes, and actually you can store quite a lot of information in that already. It's currently a centralized system, but we are working on some new approach to distributing RDF graphs in a cloud kind of way. And then so far, the most of our work was on efficient materialization. And in particular, these current systems have like 16 real cores with hyper-threaded extended to 32 cores. And actually, I also tried this out on courtesy of Oracle on one of their machines with 128 cores and 1,024 cores. And obviously, the key question is, how do you do efficient materialization if you want to use these resources efficiently? Then some of the stuff that we were working on is also on incremental maintenance, for which we've actually developed a new algorithm. And then the store supports Sparkle query answering, but that is, let's say, our weakest point at the moment. Our focus was on materialization, and the queries that you need to evaluate during materialization aren't really that difficult. No aggregates, no, just very simple conjunctive queries. So our query planning currently is really bad, and but we have some ideas on how to go about this. So what I'm going to do in the rest of my talk, I'll just very briefly give you a very high-level overview of some of the techniques that we've been working on so far. And what we started up with is parallel materialization of DATALOG. So the idea here is you support arbitrary DATALOG rules with arbitrary levels of recursion, so it's not enough to just fire the rules once, you have to keep firing them until you reach a fixed point. And again, the setting is you have this main memory machine, centralized machine, and you have lots and lots of cores which you want to use somehow effectively. And because of the latter, what you need to do is you need to somehow assign workloads to threads evenly. And that's actually not as trivial. One obvious solution is to say, okay, well, if I have, several rules which are completely independent, I could run one rule on one thread, another rule on another thread, but the fact is, in semantic web, rules are quite highly interdependent, so you very rarely get into this situation where rules are completely independent. Then what you can do is you can partition rule instances. So you say, if I map the variable x to an object which modulo number of threads equals I, then I evaluate this rule instance on thread I. This is something that has been studied in the literature also quite in depth. The problem with this is that if you have a static assignment of rule instances to threads, then you are susceptible to data skew, and again, there is no guarantee that you'll have equitable workload. And then, so what you actually need is you need some kind of dynamic assignment, which you can actually achieve in a very cheap way. And then another problem is that during materialization, you're essentially continuously querying your data and updating, querying, updating. And that's actually quite different to more common query-oriented workloads where you can sort your data, and then you can assume that for the most part, yes, you'll have some kind of small updates. But for the most part, your data set stays fixed. And then you can store these updates somewhere else. Whereas here, you constantly have to keep adding lots and lots of data to your data store. And then the problem is that these updates, because you're doing it in parallel, they occur on multiple threads at the same time. And then you have to actually efficiently parallelize that. And of course, in order to efficiently evaluate these queries, so what queries am I talking about? I mean, every rule body is essentially a query, basically, which then you have to evaluate. You need some kind of indices. So now the question is, how do you do that? How do you efficiently update these indices? And there is a paper that describes some of our basic ideas. I'm now just very briefly going to give you an idea of the actual algorithm and the approach. I'm not going to go into all the details because obviously I can't achieve all that in a 20-minute slot. And also, I'm going to first pretend that we are doing this on one thread, and then I'll tell you how we can achieve the parallelization on multiple threads. So this is a very simple example. You have your facts. So I'm writing this as, in DATALOG notation, not necessarily in RDF notation. I hope this doesn't really confuse you. I mean, it's kind of the same. So I have a bunch of facts in my database, and I have one recursive rule. The rule is recursive, so this means I can't fire it just once. I have to keep firing it until I derive all the consequences. And now what the algorithm essentially does on just one thread will be the following. It's actually sort of the obvious thing. You extract a tuple from the database. You say, okay, the first tuple is this RAB. I find the place in the rule where I can plug this tuple in. And then I get a subquery, which basically consists of all the remaining atoms in the query, where I've actually replaced the variables which I could match to this atom, and then I evaluate this subquery. And I add the results into the database, the obvious thing. But, so the point is that if you look at this query here, there are two ways to apply this rule. You can either extract RAB and map it here, or you can extract AA and map it here. You will get the same result both times, but the point is you will be doing this work twice if you do it in that way. So there is this well-known technique, semi-naive data log evaluation. So in order to capture this idea, what you basically say is, I'm going to now evaluate the subquery, but with respect to the tuples that are above the one that I've just extracted. Now, because in this particular case, this A of A occurs below the tuple that I've just extracted, I don't actually derive anything in order not to do this redundant work. So this is, let's say, a minor optimization, which is actually quite important in practice. It makes quite a big difference of this natural approach, pick a tuple, evaluate the rule. So this essentially means that while I'm going through these tuples, I don't add anything to the database. And then only when I get to A of A, I then match this to this atom here. I get a subquery like this. And now I can map this subquery to the atoms above the current one, and I finally get the consequences, A of B and A of C. And I just continue in that vein. So it's actually quite a simple algorithm, but what you can see here is you need to be able to restrict your matches with respect to the previous data somehow. So that's kind of one important feature that you have to support to be efficient. Now, how do you parallelize this? Well, you can actually, so what this algorithm does, it essentially decomposes this materialization process into a large number of subqueries. Each subquery corresponds to each of the tuples, and what then you can do is, you can send each of these subqueries to whatever thread is currently waiting for work. And this is actually a very nice way of parallelizing computation, because all of these subqueries are fully independent. Because you match your atoms to whatever comes above the currently extracted atom, that part of the database won't change. So you're not affected by what any other thread is doing at the moment. And you can just evaluate this query without any kind of waiting on other threads on their results or anything. So you basically get partitioning of rule instances to threads dynamically and with very little overhead and with very little thread synchronization. Now, as I said, the next part is, well, you've derived whatever you need to derive. Now you have to actually write this into the database. And that turned out to be by far the most complicated aspect of this work, which required some new way of indexing RDF. I don't have the time to really explain the data structures in detail, but the main idea is that what we use is we use hash indices. Why hash tables? Because hash tables are somehow naturally parallelizable data structures. You basically hash to the chances are the different threads, when they want to write a tuple, they will hash to different areas of the hash table, and then they can update these different places in the hash table more or less independently. And we've actually developed a bunch of algorithms for maintaining these hash tables in what we call mostly lock-free fashion. So lock-free basically means that if one thread fails to make progress for some time, other threads will still make progress. So this means at any point in time, at least one thread does something useful. Now, mostly is simply because there were some corner cases in which we actually had to use locks, otherwise it would get all way too complicated. But for the most part, this means that there is really no waiting in the system. And then there was also some optimizations about reducing thread interference, because even if your algorithm is lock-free, if threads end up writing into the same location, you'll get cache coherency problems. The same cache line will travel between various processors and so on. So we try to actually optimize that. All of these details can be found in the paper that I showed before, and here are some results. So our main goal with this work was to see how well we scale with a number of threads. So this was done on a machine, these tests were done on a machine which had 16 physical threads and 32 virtual threads via hyperthreading. And on 16 threads for this Claros L dataset, at this time I didn't know actually about LDBC, so we hacked together our own datasets. But I'm actually looking very much to using your benchmarks. But anyway, for this Claros L dataset, we got on 16 threads speed up of about 13.9, I think. And then on 32 virtual threads, we got speed up of up to 20, which is fair enough. And then on some data sets, it's not that good. On this one that is the worst, this is DBpedia. It turns out that there is very little to be inferred there. So the process finishes very quickly, and there is no chance for any parallelization to actually occur. But the whole point is that this approach actually does seem to work really well, to parallelize computation really well. Last year, I spent some time in California visiting Oracle, and they allowed me to use one of their super-duper machines, Spark T5, with 4 terabytes of RAM, 128 physical cores, and 1,024 virtual cores via hyperthreading. And these are the general results. So on some data sets, we got speedups between 51 and 142 times. We were able to handle Lubum 140K, which I think it used about half of the available RAM. So it was 8 billion triples, materialized to almost 11 billion triples. And with 128 threads, we got inference rates of about 4.84 million triples per second. We're actually going to repeat these experiments very shortly, and we hope to submit the paper to ISWC. The next thing that we did is same as. So all of you, I'm sure you know what same as is about. You can say 2 objects are equal, and then you have the problem that, if these 2 objects are equal, then whatever holds for one object has to hold for the other object, and that can actually create quite a lot of redundancy in your database. And there is one well-known way of dealing with same as called rewriting, where you basically make a mental note that these 2 or n objects are equal, and you replace replace any of those n objects with one object that you've actually designated as the representative of your equivalence class. And I mean, this is not something we've invented. This was used in GraphDB, Oracle's system, WebPy, and so on. The point is that, again, so there were several issues that we had to handle there. One was, how do you actually parallelize materialization when you do this kind of stuff? And that required some extension to our log-free data structures. I haven't got the time to go into the details here. But then what you might also find interesting is query evaluation. So now you do this materialization using rewriting. You have only representatives in your actual data, and you want to evaluate queries, and you have essentially two options. One is, when you evaluate a query, you virtually expand the data. So you say, if A is equal to B, and I have some information that A is of some type of, is a member of some class, then you sort of return both A and B as the result. But this is inefficient because your query evaluation still works on this expanded data. What you can do as an alternative is you can try to evaluate the query on the compressed data and expand the result. And the hope is that that's going to be much more efficient because the result is hopefully much smaller than your data set, and then the amount of expansion that you have to do is much less. But the point is that such a straightforward approach turns out to be incorrect, because you might not be counting the triples correctly, and Sparkle has the back semantics, where the number of occurrences of a particular triple in the result set matters. And there are actually cases when if you use built-ins, like filter and bind, you might actually get incorrect answers. I haven't got the time now to go into the details, but this paper that you can see here actually contains a couple of examples that demonstrate the problems, and also outlines a possible solution. And the obligatory, again, evaluation slide. I'm not going to go into the numbers. I mean, the general message is, yes, it's really worth to do this rewriting. You can get speed-ups of 30 very easily over not using the rewriting. The only thing that I found here quite interesting is that the speed-up of using rewriting can be much more, can be many more times than the decrease in the amount of data. And so this means, like, for example, you have the decrease in the amount of data is 2, but the speed up is 4. The reason for that is simply because the performance of materialization is not so much determined by the number of triples that you derive, but more so by the number of derivations. And while this equality causes a quadratic blow-up in the number of triples, but a cubic blow-up in the number of derivations. So therefore, if you use rewriting to reduce the number of triples by a quadratic factor, you can actually get a cubic increase in performance, which was obvious in retrospect, but actually quite surprising. I mean, I didn't think about it before. And the last thing that we did is we also worked on incremental maintenance of materialization. So obviously you have some changes in your input data, and now you have to either start from scratch, which we call rematerialization, which obviously if things take hours, you don't want to do that if you change only a few triples. Or you can actually try to update your existing materialization. Now, there is a very well-known algorithm called the DRED, the delete and rederive algorithm, published, I think, in the early 90s. And to our surprise, I mean, this seems to be the state of the art so far, especially if you talk about, recursive rules, full data log, basically. So how does the DRED algorithm work? So here is again a very simple example. You have two facts in your input data, A of A and B of A, both of which derive C0 of A. And then via all of these rules, you basically say C0 implies C1, C1 implies C2, Cn, and so on in a cycle. Now, the way the DRED algorithm works is the following. Let's assume that we want to delete A of A. The DRED algorithm then says, let me first delete anything that I could ever possibly derive from A of A. And this is done by slightly modifying the program in a specific way. So you basically say, well, if A of A gets deleted, then C0 of X might get deleted. If B of X gets deleted, then C0 of X gets deleted, and so on, basically. So you propagate deletions through the program. And that essentially means that in this particular example, you end up deleting all C0, C1 to Cn of A. And then in the second phase, what the DRAD algorithm does, it rederives all those facts which are still derivable after this deletion. Now, all of these facts are still derivable because they follow from B of A. There were two ways to derive B of A, either from here or from here. But in this particular case, you will then be actually deleting the whole database and then rederiving the whole database. Now, obviously, this is, an example constructed such that really demonstrates, the absolutely worst case. But the fact is, this is what we've noticed. We initially implemented the DRAD algorithm in RDFox, and we noticed that that actually does happen quite a lot in practice, even for small updates. And the reason for that is, in semantic web, the rules are not written by humans, but rather humans write, these various axioms in OWL ontologies, and then that gets translated into rules. And when you write your axioms, your domains and ranges and whatever, you don't necessarily think about the inferences. That essentially means that the rule set that you get is highly recursive and highly redundant in a sense that you can derive the same fact in many, many different ways. And that basically means if you now use this idea of, okay, if I delete a fact, let me delete all of its consequences, what tends to happen is you propagate deletions throughout the entire data set. And this was something that we saw was quite inefficient. So we developed an alternative algorithm, which we called BF, backwards forwards algorithm. And the idea is to somehow combine, backwards and forward chaining. So the whole idea is actually relatively simple. I don't have the time to go into all the gory details here. But again, let's try to delete A of A using this BF algorithm. At this point, I say, okay, let me check right away, can I derive A of A in any other way? Well, there is no rule which actually derives A of A, so I say no, and then I say, okay, this fact really gets deleted. Now, just as in exactly the same way as in the DRAD algorithm, the question is, can I now see what A of A can imply? Well, it can imply, in this case, C0 of A, because there was that one rule. So that step is exactly the same as in the DRAD algorithm. But before now I declare this, so let me delete it and maybe rederive it later, I try to immediately produce a proof. Now the way you can do this is you can now try to backward chain. And in this particular case, if you use backward chaining, you say, okay, C of A maps here, you get B of X, and then you basically say, okay, B of A is in the database, so therefore this fact stays, and therefore C0 of A stays, and therefore there is nothing else to do. Now, this is a simple idea, but actually it gets much more complicated because these rules in the backward phase can be recursive. So you don't really do backward chaining. You do backward chaining just to determine which explicit facts will contribute to your potential proof, and then you use another forward chaining phase to actually find that proof base. So it gets a bit more complicated, but such is life. And what we also did is we also extended this algorithm to work with this rewriting, because if you do rewriting, you handle same as using rewriting, then you can't apply the DRAD algorithm directly, simply because you have your rewritten data, and that's not compatible with what the DRAD works on. And also, equality tends to be very prolific. Due to equality, you end up, everything ends up depending on everything. So the DRAD algorithm again is quite bad, because when you delete something, you will now really delete the whole database partly through equality. Our version of this algorithm turns out to be much better on these kinds of situations. So these are the results for the basic algorithm. The equality version is still under review, actually. So we can actually handle quite significant updates. So for example, for UOBM, if we have 133 million explicit tuples, and we were able to, so we tried to find the break-even point where it's more efficient to rematerialize rather than to actually do incremental updates. I mean, there's always going to be this break-even point simply because, the more data you delete, the less there is to rematerialize. And, for example, in this case, this break-even point was about 10 million tuples. Here it was about 68 million tuples. I mean, quite substantial, deletion sets. But then, again, if in some of these cases, when the rules are really highly recursive and highly redundant, and especially when they connect individuals in a sort of a clique, basically, then this algorithm also can have some problems. Again, no time to discuss this now, but we have a very in-depth discussion of the kinds of problems that occur in the paper. And I mean, the DRED algorithm is also susceptible to this. So our take on this is that in order to do efficient updates, we will probably need to analyze special kinds of rules, and then for these special kinds of rules provide, custom-made incremental maintenance approaches. And the conclusion, so currently one of the big things that we are interested in is to do a data distribution layer, and we had some promising very early results, but nothing I'd like to actually talk about yet. And we are now actually implementing it, and then we hope to actually evaluate this. Another thing that we are really interested in is to improve our query planning, and in particular, one big problem that we were facing is joint cardinality estimations, which are usually done, as far as I could see, using one-dimensional histograms. I was interested in doing some kind of n-dimensional histograms in order to keep track of, the actual distribution of the correlation between subjects and objects in RDF triples, which seem to be quite important for precision. And also, I'm also interested, I don't know whether you've heard of, in the theoretical database community, there has been a lot of work on queries of bounded tree width, which are queries that actually can be efficiently evaluated, in a purely theoretical sense, very efficiently evaluated, i.e. polynomially. But then the question is, can you actually use these theoretical results in practice? And we did some work on that, and we still don't have an answer yet, but it's something that we're interested in working in the future. So that's all. Thank you very much for your attention.
Thank you. So we don't have time for one or two questions.
Anyone? Who are you? As you know, LDBC is providing both data sets and queries that are open source and freely available for scientists to do whatever they want with them. How do you think this could just help you in terms of testing your research? Do you think that would be a good choice for the type of problems you are trying to solve?
Absolutely. I mean, I actually was quite interested in what I saw here, and I'm interested in joining the LDBC because the problem is, you take your data set and you run your evaluation, but there's always this nagging feeling that, it's not really you haven't really tested your system, you don't really know, whether it was good, and you're always susceptible to somehow attacks in conferences, basically. Like, why did you use this? Why did you? It would be so much easier if I could reduce my, test setting section, even from a purely space point of view in conference papers. I use LDBC. It's well known. Go and ask them about this, very, very useful, yeah.
Thank you.